Jai Hind everyone. I am Jyoti Sharma once again taking a special lecture on the topic three-phase AC system analysis, which is under the unit 2, which is AC system analysis for the subject basic electrical engineering, which is there in the first year of AKTU. Okay, coming to the topic three-phase AC system analysis, right? Now, starting with the generation of the three-phase supply system. How this three-phase AC supply system is being generated. Earlier, we must have seen in case of single phase, how it is being generated, right? The generation process is similar as that for a three-phase as that for a single phase. The only difference which can be seen over here compared to a single phase is here we'll be having three coils. We'll be having three coils here. One is this coil, one is this coil, one is this, one is this, and one is this. So, we'll be having three coils instead of the single coil which we used to have it in case of single phase. So that now when these three coils rotate in the vicinity of the magnetic field created by the two magnets we have taken, right? Two pole system, one is north, one is south. When I make these three coils to rotate in the vicinity, if at all I am having two magnets, obviously I will be having a magnetic field being created from north to south in this way. And in this, when I make the three coils to rotate, obviously according to the Faraday's law of electromagnetic induction, there will be the flux cut experienced by the coils, there will be an induced EMF in the coil given by minus n d phi by dt, right? The expression what we have derived in case of single phase, the same expressions will be getting in case of three phase, right? But here we are having three coils. So, just imagine that if at all there is a single coil, right? The very first coil we are naming it as A1, A2. This is the very first coil. How the EMF would be induced in this very coil, right? So, we have seen this is the reference position. At this very instant, right, the magnetic lines of forces will be directly in parallel with the magnetic lines of in parallel with the magnetic field. So, there will not be any flux cut. So, the EMF induced at this particular instant would be 0, right? When I make it to rotate with a certain angle, right? According to that, when I make it to rotate, I am talking about the coil A1, A2. When this A1, A2 coil, this single coil, this is my first coil, right? When this A1, A2 is rotating at various instants throughout 360 degree, there will be an EMF induced in it, and the cycle what will be attaining, that will be a sinusoidal wave, a pure sinusoidal wave, right? Starting with 0 as its origin, right? Now, coming to the another coil which is displaced by 120 degree from the earlier coil, right? The another coil is B1, B2. This is the another coil, and the mechanical difference and the electrical angle between the two coils is 120 degrees. If that is so, it can be very easily understood that this coil itself, to reach the reference itself, it has to rotate by 120 degree. That means obviously the EMF induced, obviously this is a coil, when it will be rotating, it will be also observing an sinusoidal EMF in it, right? But while rotating, to reach the reference itself, it has to travel 120 degree. That means the EMF induced in the coil B1, B2 will be lagging A1, A2 EMF by 120 degrees, right? So, after 120 degrees, this another wave will start. So, if at all I say this is phase A for the coil A1, A2, phase B for the coil B1, B2. So, the phase B will start after 120 degree. We never mean to say that there isn't any EMF earlier to that, or there isn't any wave earlier to that, right? But the sequence in which these waveforms attains their zero or their positive maximum is being called as phase sequence. So this is going to decide what will be the phase sequence, which will be the most leading one, which one will be the most lagging one. Okay, now, so we have done up to 2 coils. Now the third coil, we can be seeing that third coil, if we'll be seeing, that is the C1, C2 coil. This is the third coil, right? So when this third coil, if you just see, once again, it is displaced from the second coil by once again 120 degrees, right? So now the EMF induced in the third coil, that will be once again lagging the second EMF by 120 degree, right? So the phase C will start, that means 120 plus 120, that means if at all I take the reference is here, R phase or A phase, from here it is 120 plus 120, that is 240. So it will start after 240 degrees. It will start after 240 degrees, right? This is phase C. So that is how we'll be getting the 3 EMFs being plotted, or the 3 waveforms which are purely sinusoidal, but each one of them would be displaced by 120 degree from each other, right? So that is being how this 3-phase system is being obtained. So in the waveform case, we have seen how the waveforms would be attained, right? We can always see now what will be the EMF, or the form of the EMF will be getting the equation. So the EMF induced in the very first coil or in first phase, that will be given by, that is the reference, so that will be having the phase as 0. So I can be writing it as En sin omega t, right? Because it's having a 0 phase, that is at reference. Now the EMF induced in B phase, EB1, B2, that will be given, that will be lagging the reference one by 120 degree. So its equation would be Em, that is maximum induced EMF, sin omega t minus 120, right? And the EMF induced in the third phase, that is C phase or EC1, C2, that will be given by Em sin omega t minus 240, because the third phase is lagging the reference by 240 degrees. Right? I may even write it as, if at all you just see, I may even draw this like this. So it can be seen that this is actually leading it by 120 also, right? The phase C, that is also leading the phase A by 120 degrees. So I may even write it as Em sin omega t plus 120. Right? But keeping this only as our reference, right, we may be giving the 3 equations as I have just written. Okay. Now, what is the reason of using the 3-phase supply system? Even though we are having a single phase supply system, and we can be having multi-phase as well, right? We can be having 4 or 6 or 12, 10, whatever. So why is this so that we are going for a 3-phase supply system? Because many of the advantages are being associated with it, right? So what are the advantages with it? It gives us, first one, the constant power, right? In a single phase circuit, the instantaneous power that varies sinusoidally from 0 to peak value at twice the supply frequency, right? So this pulsating nature of the power is objectionable for many applications, whereas in case of a 3-phase balanced supply systems, the power applied or the supplied at all the instants of the time is constant, so that its operating characteristics for all the 3-phase apparatus in general are comparatively superior, right, compared to a single phase supply system apparatuses. Also, second important, it gives us the greater output, a 3-phase system. Right? If at all I compare a 3-phase AC machine and a single phase AC machine of the same size, right? So it can be seen that the output of a 3-phase AC machine would be nearly 1.5 times greater than that of single phase, right? Or in another way, I may even say it as, if for the same rating of, if at all I design a same rating of 3-phase AC machine and a single phase AC machine, in that case, this 3-phase AC machine would be comparatively much more compact or smaller in size, right? So that is one of the advantage. The another one is the 3-phase AC machine is much more motors, they are much more smaller, they are less expensive than the single phase, because as the size is smaller, they require less material, right? However, you know, the 3-phase AC machines, if at all I say, these are in fact self-starting, right? 3-phase induction motor or AC machines, these are all self-starting compared to single phase. Single phase induction motor requires, because it is not having a rotating magnetic field, so we need to provide various methods, likewise capacitor start, capacitor run, or resistive split method, right? Many of the methods, shaded pole method, we have to go for to make them to start, right? But that is not the case for a 3-phase AC machines, right? So it is cheaper, it is self-starting. Another one, power transmission economics. So if you just see, the transmission of the electric power by 3-phase system is cheaper, and that of a single phase, that compared to a single phase system. Even though the conductors required for a 3-phase system are 3 and for a single phase it is 2, right? So that is the power transmission economics. These are the certain uses, or I must say the advantages of 3-phase system, which makes it much more readily usable compared to a single phase system and other multi-phase system, right? Now, we have just seen, in case of generation, if you just see, right, we were having 3 coils. Say this is our phase, right? What we were writing it as A1, A2. This is first phase, right? The second phase, that was that was B1, B2, that was lagging the initial phase by 120 degree. Then the third phase, that was C1, C2, that was once again lagging it by 120 degree, right? Each one of them are lagging by 120 degree, right? In that case, right, if at all you just see how many terminals we are having. We are having 1, 2, 3, 4, 5, 6. We are having 6 terminals available with us, and we want to have a 3-phase supply system. What are the possible ways in which these 3-phase system, these 6 terminals can be connected, right, to form a 3-phase system, or 3 terminals being taken out, 3 or 4 terminals being taken out. So we know that, we have seen that in first unit as well, right? The connections can be now, right, either a delta connected system or a star connected system, right? It can be a delta connected system or it can be a star connected system, right? Prior to that, or prior to going to how the star and delta connections are being done, we must be familiar with certain terminologies. Likewise, what is a balanced 3-phase supply system, right? A balanced 3-phase supply system is the one where all the line voltages and all the line voltages are equal, all the phase voltages are equal, the currents are equal, right, in all the phases and in all the lines. So that is a balanced 3-phase supply system. What is a phase sequence? This is the second terminology we must all be knowing. What is a phase sequence? I'll be using it again and again, right? So the sequence in which, or the order in which, the individual voltages, what are the 3 voltages for the 3 phases, right? For R phase, for Y phase, for B phase. So the three phase voltages, how they, the order in which they attains their zero or positive maximum, that is being called as phase sequence. As we have seen in the waveform, the very first wave which attains its zero or maximum is the R phase. After it 120 degree, the another wave which is Y phase will start, and after that the B phase will start. So the phase sequence is R, Y, B. It is understood that if the phase sequence is RYB, I am saying that the phase sequence is RYB, it means that the R phase is the most leading phase. The Y phase would be lagging the R phase by 120 degree. The B phase would be lagging R phase by 240 degree, or I may say B phase would be lagging Y phase by 120 degrees. Okay. Now coming to the two connections what we were saying, right, or the types of loads we can be connecting. So it can be either star connected or it can be either delta connected. So first going with the star kind of connection, right? If you just see, this is the star kind of connections, right? Or how can we say that this is a star kind of connection? It is forming a star formation, right? And in this, if you just see here, these are the three coils what we are having. This is A coil, or we are calling it as R coil. This is B coil, this is C coil, right? These are the starting ends, finishing ends, starting end, finishing end, starting end, finishing end. A star connection is the one where the finishing end of all the three coils are being taken together, and that point is being called as neutral, right? That neutral wire can be taken out or cannot be taken out depending upon our application requirements, right? So likewise, we are having now three wires coming out, or three phases coming out, that is R, Y, B. Neutral wire is there that can be taken out or left, right? Similarly, delta connections, if you just see that, we know a delta connection, it has to be a closed loop, right? So the starting of the first, this is the starting of the first, the finishing of the second, the same, the finishing of the first has to be the starting of the second, right? And then the finishing of the second has to be the starting of the third, and the finishing of the third has to be the starting of the one. So that we are getting a delta connection, right? Here we won't be having any neutral, right? So we'll be having three wires being coming out. One is R, Y and B. This is a three wire system. Now seeing what are the relationships or how this connection goes for a star balanced, star connected supply system. For this, we need to know certain things, right? Now, if you can see, this is once again the star connected system, right? This is the R phase being connected, this is Y phase, this is B, right? Now, here we can be seeing, we are having two terminologies for this, right? Two kinds of voltages. In case of single phase, we used to have a single voltage, that is line voltage, or we are calling it as VRMS, which is nothing but we are calling it as, it is the voltage between the particular phase and the neutral, right? Okay, but here if you just see, this is the neutral point, right? Now if at all you see, this is my R, this is Y phase and B. Now the voltages between any two lines, that means R line and Y line. What is the voltage between R and Y? That is VRY. This voltage, VRY. So this is one of the line voltage, right? Can I be having another line voltages? Yeah, I'll be having another line voltage that will be between Y and B. That will be called as VYB. This is VYB. I can be having another line voltage which is between B and R, that is VBR. Remember, I am following the phase sequence. What is the phase sequence? That is R, Y, B. So, what are the line voltages I am having? What are the line voltages I have written? The very first line voltage, that is between R and Y. That is between R and Y. That is VRY. What What is the another line voltage? That is between Y and B. That is VYB. What is the last line voltage? That will be between B and R. VBR. I am following the phase sequence. Right? So, the three other line voltages, that is VRY, VYB and VBR. If it is a symmetrical system, then all the line voltages would be same. A balanced symmetrical system, then all the line voltages are same, and I am representing it with VL as the letter, line voltage. Okay. Similarly, another terminology which is being used, that is V phase. That means phase voltage. The voltage between the line and the neutral, right? Or for a particular phase. If you just see, this is the impedance or this is the load for our phase, right? So, whatever is the voltage across this, that will be the phase voltage of our phase, right? And which is this impedance is being connected between the line and the neutral. Fine. In case of star, right, it is connected between line and neutral. Or I may be saying whatever is the voltage across that particular load impedance, that will be its phase voltage. How would I represent it? So, I will be writing it as VRN or ERN, between R and N. Similarly, the voltage between Y and N, that will be called as VYN or EYN. Similarly, what will be the voltage between B and N? That will be EBN or VBN. So, I am having the three phase voltages. Once again, following the phase sequence, VRN, VYN and VBN, the three phase voltages I am having. Once again, if all the phase voltages are same, then it will be a symmetrical supply system, right? Now, do I have any relationship between these two? Prior going to that, right, as the voltages are there for the line values, for the phase values, do I have currents also like this? Yeah, I do have current like this, right? Just go for it. What will be the currents, right? So, the currents which are flowing in the lines here, this is IR flowing in R line, this is IY flowing in Y line, IB flowing in B line, right? So, these are the line currents, IL, the line currents are IR, IY, IB. These are line currents. Once again, symmetrical system, all the line currents are equal. Fine. Do I have phase currents also? Right. I do have phase current. Where? Where the phase is there. Where is the phase? The impedance is, the phase is where the impedance is being connected, right? That means here. So, whatever is the current flowing in this impedance, that will be my phase current. And you can see it nicely that for a star connected system, whatever is your line current, that will be flowing in this impedance, or that will be my phase current. Similarly, whatever is the current flowing in this line, the same current would be flowing in this impedance. The current which is flowing in this B, that will be flowing in this. It means what? For a star connected system, the phase current is equals to line current. We have to remember this. This is a very important property, that the line current is equals to phase current. Do I have a relationship between phase voltage and line voltage as well? Right? Just go for that. For a line voltage and phase voltage, if you just see, we have just gone, if you just see the diagram, do I have any relationship between the line and phase voltages here? Right? Do I have any relationship between line and phase voltage over? Yeah, I do have. What is that? Take any one phase line voltage, right? How can I write that? VRY. Can't I write that VRY is equals to VRN Can't I write it as VRY is equals to VRN minus VYN. If you just see, right, VRY, the voltage between these two is equals to the algebraic sum of these two, right? Or I may be writing it for any other phase voltage as well, for any other line voltage as well, right? So if you just see VRY is equals to VRN minus VYN, right? Going for the phasor diagram of it, right? So I need to draw the very first phasor, that is the phase voltage VRN. So if at all I am considering VRN to be here, right, where would be VYN? EYN would be lagging the first voltage by 120 degrees. So the another one has to be here. VBN, it has to be once again lagging by 120 degrees, right? If that is so, now where should be ERY? If ERY has to be there, it is the phasor sum of ERN minus VYN. That means this is positive EYN. I have to go negative. So negative is where? Here. Now the phasor sum of these two will give me VRY. Similarly, the other two, I may be having VYB as the phasor sum of EYN minus EBN, right? I may be having VBR as the phasor sum of EBN minus ERN, right? As it is a symmetrical supply system, I may be showing it for only one, that be applied to all. It is a symmetrical supply system, all the phase and line voltages are same. If that is so, how can the magnitude can be known for VRY? So it can be known that ERY is equals to twice of EPH. Why? Because both the phase voltages, these two are the phase voltages, right? They are equal. Twice of EPH, cos of 60 divided by 2. What is this total angle? This is 60, right? Divided by 2, that is 30. So the expression will be getting, that will be ERY is equals to root 3 times the EPH. The same can be derived for rest of the two. Right? It means that what is ERY? That is my line voltage. So line voltage is equals to root 3 times the phase voltage. So what are the two relations what we got? One is that for a star connected system, the line voltage is equals to root 3 times the phase voltage, and also the line current is equals to root 3 times the phase current. Right? Now moving on to delta. In case of delta connected system, right, how the relations are verified, right? If you just see, this is a delta connected system we have just discussed, right? Once again, I can be having the phase and line current, phase and line currents, phase and line voltages, right? So if you just see, where would be the line voltage? Say this is RYB. So this will be VRY. This will be VYB. And this will be VBR. These are the three line voltages, right? Also, where would be the phase voltage now? I don't have any neutral over here, right? So how would I be deciding where is the phase exactly, right? But I know that the impedance being connected is in one phase, right? That means this is the voltage across this will be giving me VR. That means R phase voltage. The voltage across this will be giving me Vy, and the voltage across this would be giving me Vb. But you actually see in the diagram, this VR is very much equal to VRY. This Vy is very much equal to Vyb, and this Vb is very much equal to VBR. It means what? It means that for a delta connected system, the line voltage is equals to phase voltage. Right? Can I say the same for the currents, that the line current must be equals to phase current? Can I say that? Right? Let's check that out. Right. Now, where would be the line currents? Where would be the line currents, right? These are the line currents. First, we will be deciding phase currents. The phase current flowing in this load, that is IR, in this is IB, and in this is IY. So the current in the lines, that will be IR minus IY. IB, this will be IY minus IR, and this will be IB minus IY. If you just apply your KCL at these points, that means obviously in this case, the line currents and the phase currents are not equal. They are having certain relationship, right? Once again, I can be plotting the currents, right? How I can plot the currents? Once again, I'll be plotting the phase currents first. So the very phase current which will be occurring according to the phase sequence, that will be IR, okay? So IR, after 120 degree I'll be having, after 120 degree I'll be having IY, and after 120 degree I'll be having IB. Now, how to have IR minus IB, which is nothing but your line current, right? You just see here, what is the relationship? IR minus IB, that is given by, if you just apply your KCL over here, that is IR minus IB will be giving you IR minus IB. So I have to go for minus of IB. IB is here, minus of IB, that is downwards. The algebraic sum of these two is going to get me IR minus IB, right? Once again, the angle between the two, this is 60, this angle is only going to be 30, right? Once again, applying my parallelogram law over here. So I can be writing that the line current I1, or I can be calling it as IR minus IB, that will be given by twice of I phase cos 60 minus 2. I'll be ultimately getting root 3 I phase. That means the relationship I am getting is the line current is equals to root 3 times the phase current, right? It means what? For a delta connected system, we have got two relations. Line voltage is equals to phase voltage, but line current is equals to root 3 times the phase current, right? Moving on to the power expressions. What will be the power, right? The active power, the apparent power, and the reactive power. And the expression for these remains same, let it be for star connected system or for a delta connected system, right? The expressions remain same, but the power doesn't remain same. If the same impedance is being connected in star and in delta, we must have seen in the star delta transformation, the power consumed in a delta connected system would be thrice the power consumed in a star connected system, right? Okay, but expressions would be mathematical expression, that is going to be same. Likewise, the power consumed, the active power consumed in a three-phase system, that will be equals to thrice the power in each phase, right? That is given by 3 into what will be the power in each phase? V phase, I phase, cos phi, where what is phi? That is the angle between V phase and I phase, right? Not the line current and the phase current, because the impedance is always the phase value, right? So its angle phi, it has to be the angle between V phase and I phase. Okay, if that is so, the expression I can be once again writing it in terms of line. In case of star connected system, the line values 3 is there, V phase that is being given by VL by root 3, I phase and IL are equal, so cos phi. So in case of line values, I'll be having the expression as root 3 VL IL cos phi, right? Reactive power, if at all I go with the same, once again I can write it as root 3 VL IL sin phi. Apparent power, I can be writing it as root 3 VL IL. In fact, in case of phase also, I can be writing it as 3 VPH IPH sin phi. Here, I can be writing as 3 VPH IPH. What will be the units? For active power, we know it has to be watts or kilowatts or megawatts, right? Basic unit. Similarly, for reactive power, it has to be VAR, volt ampere reactive, kilovolt ampere reactor. And similarly, it has to be volt ampere VA. The same terminologies follows for a delta connected system. The terminology is same, right? Now, taking the question which has been occurred in university exam 2016-17, that is, A balanced star connected load of 8 plus J6 ohms per phase is connected to a 3-phase 400 volt supply, right? Find the line current, the power factor, the 3-phase power and the 3-phase volt ampere, right? If that is so, first, it is a balanced star connected load, right? What is the value of the load? The load impedance ZPH, that is given by 8 plus J6, right? I can convert that into polar form, right? That will be 10 angle 36.86. What will be the phase voltage? This is given to me. The value which is being given to us is the line voltage, that is 3-phase 400 volts. What is this value? This is the line value, right? For a star connected system, the phase value is equals to VL by root 3, right? What is VL? 400. 400 by root 3, that is 230.94. Fine. If that is so, what will be the phase current then? What is the very first thing I need to know? The very first thing I need to know is the line current. But remember, as the impedance is always phase value, right? It can be derived by VPH upon IPH. It can't be derived by VL upon IL. That is the phase value, right? So, it means that it has to be always the phase current which has to be found out, let it be star system or delta system, right? So, the phase current that can be given by V phase by Z phase. Yeah, right? What is V phase? That is 230.94, taking it as reference with an angle of 0, right? And Z phase, that is 10 angle 36.86. So, I'll be getting the phase current as 23.094 with an angle of minus 36.86 amperes. So, this is my phase current. But the question is asked for the line current. If you just remember, we have derived for a star connected system, the phase current is equals to the line current. That means the line value current is also going to be 23.094 with an angle of minus 36.86 amperes. Right? Next is, what will be the power factor? Right? Cos phi. So, we already know what is cos phi. We have derived ZPH and we have written it in polar form, 10 angle 36.86. So, whatever is the angle of our impedance, that is going to be phi. That means cos of 36.86, that is going to be 0.8, obviously lagging, right? It is 8 plus J6, that means the load is inductive in nature. So, the nature of the power factor has to be lagging. Then the active power, I can be deriving it in line terms, I can be deriving it in phase terms, right? So, in line terms, it has to be root 3 VLIL cos phi, right? Root 3, what was VL? VL, we were knowing it as 400 from the data. IL, we just derive it as 23.094, right? Cos phi, we just got it as 0.8. It is going to be 12.8 kilowatt or 12,800 watts. Fine. The last thing which has been asked is the 3-phase volt ampere. 3-phase volt ampere, the apparent power, right? So, the apparent power is given by root 3 VLIL. I told you the values can also be determined in phase values as well, right? The answer would be same, only the expressions would be different. So, I can be find it out as 3 VPH IPH. Similarly, the active power can also be found it out as 3 VPH IPH cos phi. Answer is going to remain same, right? Okay, root 3 VLIL. So, that is root 3 VL is 400 and IL is 23.09, which is going to be 16 kVA. Going for another example, that is for a delta connected system or delta connected load of 12 plus J9 ohms is connected to a 3-phase 400 volt supply. Find the line current, the power factor, power drawn, reactive volt ampere and total volt ampere. Okay. So, the very first thing, this is a delta connected system. So, we need to remember the relations are opposite. Fine. We need to find line current, but always remember for finding line current, first we need to know what is phase current, right? So, for finding phase current, the Ohm's law for a 3-phase AC system, that is given by V phase by Z phase. What is V phase? Go for the data. 400 volts. Is it the phase voltage which has been given to us? No, that is the line voltage being given to us. But for a delta connected system, the line voltage is equals to phase voltage. We have derived, right? Although in case of the question, the details which has been given to us is in line form, right? 400 volts. But we know that the line voltage is equals to the phase voltage in case of delta. So I'll be considering it as 400 with an angle of 0. Z phase, it has been given to us as 12 plus J9. I can convert that into polar, right? That is equals to 22.4 with an angle of 57.72. So the I phase, that is going to be 17.85 with an angle of minus 57.72 ampere. This is my phase current. But the question asked is line current. Is phase current equals to line current in case of delta? No. That is in case of star. So in case of delta, what is happening? Line current is equals to root 3 times the phase current, right? I got the phase current, right? So root 3 times, that is root 3 into 17.85 will give me 30.9 amperes as the line current, right? Next, what will be the power factor? Once again, the power factor cos phi. What will be phi? Where should I get the phi? Right? The phi can be determined from either the angle of the impedance, or I may even find it out with the angle between the phase voltage and the line volt, the phase voltage and the phase current, right? But the impedance angle, that is 57.72. So cos of 57.72, that is 0.534. What will be the nature? Will it be lagging, leading? See the impedance, that is 12 plus J9. That means it is inductive, right? Plus J, that means it is inductive. Inductive means the power factor has to be lagging. So it has to be 0.534 lagging. Okay, the another one, power drawn. Which power drawn? Obviously, active power drawn, that can be given by root 3 VL IL cos phi. I may even find it out with the formula V phase I phase cos phi, thrice of that, right? But we are doing it with root 3 VL IL cos phi. The answer is going to be same. Root 3, what will be VL? 400. What will be IL? We just derived it, IL as 30.9. Substitute that. Cos phi, we just find it out as 0.534. So the active power is going to be 11.431 kilowatt. Don't forget to mention the correct units of these powers, right? Then the reactive power is being of reactive volt ampere, that means reactive power given by root 3 VL IL sin phi. Once again, root 3 VL is 400, IL is 30.9, sin phi, cos phi is 0.534, so we can find the cos sine of this angle, that is 0.854. So that the reactive power becomes 18.08 kVAR, kilovolt ampere reactive. The last thing, that is apparent or the total volt ampere or the apparent power, that is given by root 3 VL IL. It is going to be 21.408 kVA. Another question can also be taken. This has occurred in the university exam 2018-19. That is, the 3 identical coils of resistance 8 ohms and inductive reactance 6 ohms are connected in delta across 400 volt supply. Determine the power factor and line current. Same kind of question. Here, instead of giving you the impedance in a rectangular form, I have given, the question has been given in distinct form, right? The value of the resistance is being given to you and the inductive reactance is being given to you. If that is so, we can always represent it in rectangular form, right? So the impedance, obviously the phase impedance, that is given by resistance of 8 ohms and inductive reactance of 6 ohms. So it has to be 8 plus J6. What would be the case if it would have been a resistance of 8 ohms and a capacitive reactance of 6 ohms? If that is so, in that case, what will be the expression? If it is a capacitive reactance, it has to be 8 minus J6. I suppose everybody remember this. But as in the question it has been mentioned as inductive, so we'll be writing it as 8 plus J6, right? If that is so, now what will be the line current? Line voltage. The line voltage being given to us is across 400 volt supply. So the line voltage is 400 volts. It is a delta connected system. So once again, the phase current would be given by phase voltage by phase impedance. Phase voltage, that is 400. Impedance, if at all I convert this, I'll be having it as 10. So 400 upon 10, that is 40 amperes. What will be the line current for a delta connected system? We have done this earlier. Root 3 times the phase current. So root 3 times the phase current, root 3 times 40, that will be 69.28 amperes. What will be the power factor? I can be doing it by R by Z, as simple as that, right? R by Z, I can be doing it as cos of, I can be converting this into over here, right? That angle is going to be 36.86, right? If at all I convert this into a polar, I'll be having it as 36.86. And if at all I do cos of 36.86, it is going to be 0.8, right? Or I may be going it for R by Z. What is the resistance? 8. Impedance I just found out is 10. It is going to be 0.8 lagging, right? As the load is inductive. Active power, root 3 VL cos phi L. Just substituting that, root 3 VL is 400. IL, we just found it out as 69.28. Cos phi, we just found it out as 0.8. So that is 36.4 kilowatt. So this is all for 3-phase AC system. The references what I have taken is from D.P. Kothari and I.J. Nagrith, which is a reference book for basic electrical engineering, and D.C. Kulshestra, that is also a reference book for a basic electrical engineering subject. Thank you all for listening me so patiently. Thank you.